Now we've seen two types of products which are valid for vectors. That's basically dot product and cross product. We've seen how both of them are actually evaluated, what is their significance, their physical significance, their geometrical significance, where they are used in physics, various properties that involve these two products, right? We've seen the entire picture of how these two products look like and what is actually happening. We will now move on to this third type of product, which is scalar triple product. The question remains still the same. Can two vectors be multiplied? We've already seen, yes, they can be multiplied in two ways. One of them was your dot product, one of them was your cross product. There is this third way called scalar triple product, and this is also a different type of product which is valid for vectors. The only thing here is it is a triple product. As the name suggests, triple product. For this you need to have three vectors. So what I will do is I will actually draw in a plane, or doesn't matter if it's in the plane or not. You have a vector A bar, B bar, and maybe one more, something like this, C bar, right? This plane is actually unnecessary here. You might have three vectors. You need to have three vectors to carry out this scalar triple product. Now that we already know what a dot product and a cross product is, understanding scalar triple product shouldn't be that difficult, because it is only a combination of cross product and dot product. Let's see how we can actually find scalar triple product. Remember, the scalar triple product is also known as box product. Scalar triple product is also called as box product. You will see why. It's called box product because it is denoted by a box. Box A bar, B bar, C bar. I have three vectors here, you can see. If I have to take their box product or scalar triple product, I denote it like this. But the question is, how do I carry out this? How is this product calculated? The answer to that is, you have two vectors A bar, B bar. First take their cross product. So this will give rise to some vector, right? A cross B is a vector. So this will give rise to a vector. And then with this vector, you take the dot product of C. So you're taking cross product and dot product simultaneously. Now I would like to post an interesting question here. Is this expression valid? The question is this expression valid? Just think for a while. The answer is no. Why is it not valid? Because A dot B, A and B are vectors, right? A and B are vectors. What is A dot B? Is A dot B also a vector? No, it is a scalar. A dot B will give rise to a scalar. So it is like some lambda. This is like some lambda. And I can't take the cross product of lambda with a vector, because you can take the cross product only between two vectors. Both your lambda and C have to be vectors. So I can take A cross B. It's valid only when both your A and B are vectors. If one of your vectors changes to some scalar, then it is invalid. Then this is invalid. So you have to keep in mind the reason why I brought this up is it will actually help you not confuse this expression with this expression. So some of you, this is wrong. Some of you might end up, taking the dot product first and then taking the cross product, basically messing up the order of the dot and cross, but that will make a huge difference. And the reason why you have to remember that this is wrong, and the way to remember that is, if you do A dot B, you will get a scalar, and you can't take the scalar, you can't take the cross product of a scalar and a vector. That's invalid. So this is what you have to remember, this particular formula. Let me make some space to give the variants of this box product. So this is one formula. Whenever you see this box, remember the first two vectors, A and B here, you always take the cross product of the first two vectors and dot it with the third vector. That's how you can remember this. Or what you can also do is, you can take the dot between the first two and cross here. That means you can also do this. Remember, this and this are the same, right? I'm not proving that right now. We will actually look at why they are same when we actually, see the geometrical interpretation of scalar triple product. That is when you will understand why this and this are the same. But for now, what I would like you to remember is you have three vectors A, B and C. Either you take the cross product of the first two and then dot it with the third one, or you take the cross product of the second and third and dot it with the first one. That's your anything you can do. Both of them are the same and both of them are equal to this box product. But what you have to not do is this. You don't take the dot of the first two and cross it with the second one. And neither you can take the dot of the second and third and cross it with the first. Both of these are invalid. You can't do these two. So just keep that in mind. So this was the first basic introduction to what scalar triple product is. Let's look at a few properties of this, of just this box, not the entire properties in detail. How you can actually change A, B and C and how that will actually change the formula. So let's look at that, and after that we will see how to actually calculate scalar triple product when your vectors are given in the component form. So we've seen the basic introduction to scalar product and this particular formula, and why it's called box product, because it is denoted by this box. Let's move into a few variations of this order now. So what if I change the order of ABC? How will that bring about a difference? So for that, just look at this. Box ABC is A cross B dot C. If I make A cross B as B cross A, then what do I have to do? To make sure that this thing remains, this entire expression remains the same, I will have to account for that by a negative sign. So minus B cross A dot C is the same as A cross B dot C, right? So both of them are the same, because this A cross B I have interchanged the order, but I have accounted for that with this negative sign, right? So this thing is still your box ABC, right? It's still your box ABC because I just changed the order and accounted for that by this negative sign. But can I write this as something like a B cross A dot C, like separately with this negative sign outside? What will that be? That will make this minus BAC box, because now it is like I'm crossing B and A and then dotting that with C in this order. So this is like box BAC. So if you can see, box ABC is equals to minus box BAC, right? So this is actually giving rise to an interesting thing. If I change the order of these two, then I'll have to account for that by a negative sign. Similarly, look at this. If I change the order of these two, then box ABC is equals to A dot minus B cross, so it's B cross C, so minus C cross B, right? Minus C cross B. But this negative sign has to be accounted for because you're changing the order. So take this negative sign outside. Now it is your A bar dot C bar cross B bar. This is B bar, right? And this negative sign is still outside. So box ABC now is minus, this is your A dot C cross B. So this is your A dot C cross B, which is equal to box ACB, right? Because if you expand box ACB, then you'll put a dot here and you'll put a cross like this, and that is what this is, right? This is box ACB. So look at this. Look at this and this. Box ABC is equals to minus box BAC and also equal to minus box ACB. So if I change the order of these two, I'll have to put a negative sign. If I change the order of these two also, even then I have to put a negative sign. So if I change B and C, even then I'll have to put a negative sign. So I would actually like to state something here, and this way you'll be able to remember it much better. Let me make some space for that. So yes, what we have looked at is if I make one interchange, then there will be a negative sign accounted for in the box. If I make another interchange here, like any of these two, or in fact for this one I made an interchange in the first two. So when I made the interchange in the first two, then I got this. When I made the interchange in the last two, then I got this. What I would also like to write is the rule that I would like to write here is if one interchange is made, then negative sign is to be taken. So fine, if you want to change A and B, there are no issues. Make changes to A and B, write box BSC, but don't forget to write this minus sign. Why? Because you are making just one interchange. If you want to change B and C, fine, you write A, C, B. But if you want to make this equal to A box ABC, then you'll have to put a negative sign. Only then it will be equal to ABC, right? The second rule that I'm writing now, this thing I'm not showing you with detailed proof as to the way I showed you for one interchange, but you can verify that for yourself, by just expanding the box product, and that is, if two interchanges are made, then no negative sign is to be taken. What does this rule mean? And why am I taking this negative sign? First of all, I'm taking this negative sign because I want to make this interchanged box product equal to my original box product, right? That is the reason why I'm putting this negative sign. But for example, if I change AB, for example here, ABC, if I change AB, and then if I make one more interchange, then that will still be equal to box ABC. So what I mean to say is something like this: box ABC is equals to box BCA is equals to box CAB. So here, as you can see, there are no negative signs. The boxes are equal to each other with two interchanges. So how have I got this from this? Let's look at that now. So basically, I'm interchanging A and C first of all. So if I interchange A and C, then what I'll get is CBA. But then if this and this have to be equal, then I'll have to put a negative sign. But then what I'll do is I'll make one more interchange. I will interchange B and C now. So if I interchange B and C, then I'm making one more interchange. So I'll have this negative, one more negative sign will come out, and that will become positive. That is the reason why this and this are equal, because to get this from this, you are making two interchanges. Similarly, to get this from this, you are making two interchanges, and that is the reason why there is no negative sign outside here. There is a plus sign. There is no sign, that means there is plus sign, right? So just verify that for yourself. If you make two interchanges, you will get this. Let's actually look at that now. So ABC. If I make one interchange, then I can write it as CBA, something like this. And then if I interchange these two, this was one interchange, and one more interchange if I make, then that will be CAB. So because I made two interchanges, this and this are equal. But remember, this and this differ by a negative sign, not differ by a negative sign, but they are equal to negative of each other. This and this are negative of each other. This and this are negative of each other. Right, so this negative of each other, this are negative of each other. So this and this are the same, right? That is what I mean to say. So this rule is coming from that. In fact, instead of two, I can also write, if I make even interchanges, then there is no negative sign to be taken. And if I make odd interchanges, then there is a negative sign to be taken, right? So remember that. If you make even interchanges in this box product, then you don't have to take negative sign. The interchanged box product will be the same as the original box product. The interchanged box product will be the same as the original box product. But if I make odd number of interchanges, something like if I just end up changing B and A, then this interchanged box product will be the negative of this original box product. Alright, so this was the entire motive of explaining you this. Let's move on to finding the scalar triple product when vectors are given in their component forms. So let's now look at when I have three vectors in their component forms, how do I then find out what the scalar triple product is? Right. So how do I find out this box ABC? Remember, this section is very important because the result that we will get from this is extremely important, because you'll not just be using that in calculating the scalar triple product, but also a lot of times in three-dimensional geometry. So in 3D geometry, you will use this result a lot of times. So that is the reason why you need to be thorough with this. So I have three vectors A, B, C. You can see them here. You can see them in their component form also. How do I find the scalar triple product? So it shouldn't be difficult now to expand it in this form. This is the formula A cross B dot C, right? If I need A cross B, I use the matrix determinant method, right? We've already seen this I, J, K. And then because it is A first, we will put the components of A in the second row, A1, A2, A3, and B1, B2, B3, right? You have to dot this with the components of C, that is your C1I plus C2J plus C3K. Now, as you can see here, what will happen is when you expand this determinant, it will be some I into A2 B3 minus A3 B2 plus some J into something plus some K into something. When I take the dot product of this with C1, C2, C3, then what will simply happen is this I and this C1 will actually multiply, right? Because you already know whenever you have to take the dot product of two vectors in their component forms, for example, something like this, and B1I plus B2J plus B3K, and you have to take the dot product of these two. You have to take the dot product of these two. What you do is A1, B1, just multiply the I components, multiply the J components, multiply the K components, and add them, right? So that is what we will do here as well. So as you can see here, we will multiply this with this, and ultimately we will be getting a term like C1 into A2 B3 minus A3 B2. Similarly, we will multiply C2 with this part and we will be getting C2 into whatever was there here. So ultimately what I'm trying to say is, when you take the dot product of this entire determinant with this, I can actually dot this part with the first row. And the result that I'll be getting is the same. This is the reason why I was opening this up and showing it to you. Let me actually make some space and show you what the final result will be. So ultimately your A1, A2, A3 and B1, B2, B3 will remain as it is, but this vectors part, that will get dotted with this. So you will have I dot this part. So let this vector be, this is your C bar, right? So I dot C bar, and then you'll have a J dot C bar, then you'll have a K dot C bar. If I dot this with I, then what will I get? I'll get C1. If I dot this with J, then only C2 will come out, right? So I'll get C2. If I dot this with K, then I'll be only getting C3, right? Then you can verify yourself. You dot this with I, these two will become 0 and you'll only be getting C1. If you dot this with J, then these two will become 0, you'll only be getting C2. Similarly, if you dot this with K, you'll only get C3. So ultimately, the final result is C1, C2, C3, A1, A2, A3, B1, B2, B3. This is the scalar triple product or your box product. So let me just quickly recap what I have done. So we had three vectors in their component forms. If I need this box product of these three vectors which are in the component form, I will simply take C1, C2, C3, A1, A2, A3 and B1, B2, B3 in this order, right? So if I have C at the last, here C will be first, and then because it's A cross B, A will be here, and because it's A cross B, B is second, so your B will be here. So remember this order, because if you mess up with the order, if you bring C here and A here, then your determinant will become negative, right? So you have to take care of that. So with this we complete. This is an extremely important result. This result that you see here, box ABC equal to this determinant, is an extremely important result. Let's move on to the geometrical interpretation of scalar triple product.